speaker is Olivier Brüls from the University of Liège. And I hope I didn't mispronounce more than one of those.
It was perfect.
Okay. And he'll be telling us about geometric numerical methods for robot simulation, control, and optimization.
Thank you very much for the introduction, and so good afternoon, everyone. I would like to thank also the organizer for the kind invitation. It's a real pleasure for me to be here and to be able to exchange with experts from different fields, from mathematics, engineering, and others. Okay, so to motivate a bit why we need models, I just recall here a number of problems found in robotics, very classical problems for which models turn out to be very useful. So for those of you who are not familiar with robotics, so the goal is usually to control the motion of the end effector here. So we represent the motion by attaching a frame to this end effector. But to control this motion, we act on the joint using motors, right? And so we have different types of problems. For example, in direct kinematics, we know the joint coordinate and we want to predict the motion of the end effector. But we are also interested in the inverse version, where we want to achieve a certain motion at the end effector and we want to find the joint coordinate. Well, these problems are very central when we do trajectory planning. Then another interest is in dynamics. Then the question is, what is the amount of torque that I need to put in my actuators to move the machine in the appropriate way? And then, of course, we have to deal with control problem. Controlling the motion is one thing, but when you have some sensitive tasks, for example, when you want to manipulate object, it's also important to be able to control the force that you exert on the environment. And models are also quite useful for other problems like collision detection. Okay, in robotics, there is also a fancy trend to use machine learning techniques. Well, in my perception, most of the potential on these machine learning methods is not on these low-level problems, it's more on high-level problems. And in order to be able to solve these problems, it's still necessary to have a good solution on the low-level problems. Okay, so machine learning methods extend the scope of application of robotics, but still we need a very efficient model in order to solve the low-level tasks. Okay, in our group, in our research lab, we are very much interested in problems related to flexibility in the joint and links of the robots, and I will motivate a bit this. So here you see in this slide a few pictures of very lightweight robots, and in these applications, vibration problems cannot be neglected anymore. So why? Because in these machines, the dynamic excitation really interact with the natural frequency of vibration. And okay, why are we interested in these lightweight robots, which have some vibration problems where there are different drivers for that? First, the cost of this machine can be reduced. Then if the weight is smaller, you can use smaller actuators. You can reduce energy consumption. Also, if you gain weight, you can achieve faster motion. And in case of collision, of course, when the robot is light, you reduce the severity of collision. But in the community in robotics, people also try to put compliance on purpose. Sometimes it's interesting to have a compliant robot for the following reasons. So first, when you have a compliant robot, you have a better control or better capacity to limit the forces that the robot exerts on the environment. Then there is also a strong tendency to develop soft robots. And in these robots, there is a direct or tight integration of sensors and actuators in the structure. So it's really based on the fact that the structure is compliant, is soft, and then it allows this type of integration. And these, I would say, compliance are also quite interesting when developing human-robot cooperation tasks. Okay, so we need to be able to account for flexibility, vibration in robots. So what kind of tools could we use? Well, here I show you an example of what I consider as really the state of the art in terms of industrial software that are used by engineers. So this is a package called SAMSEF. It's developed by Siemens. I mentioned this software because it originates from my own university, and then currently the company that developed this software has been bought by Siemens, and so now it's part of the Siemens solution. So what can we say about this? It's a finite element package. What can we say about it is that it has the capacity to model a full machine, including some very detailed, I would say, very detailed representation of the components. So what you saw in this car model, you can represent the full motion of the car, but inside this full vehicle model, we include the detail about this component, which is a differential. And if you looked at the model here, it represents really all the interaction in the differential between all the bodies. You have contact, you have flexible bodies, you have a lot of dynamic phenomena. And then with this type of model, or with this type of tool, it's possible to account for the influence of this specific component on the driving capacity of the vehicle. Another application area for this type of nonlinear finite element package is the wind turbine area. Here you see an example of a wind turbine. Again, the same story. It's possible in a unique or a framework to include in the same simulation all type of components. So some of them are rigid, some of them are flexible. You have these transmission lines, you have the aerodynamic loads. So all these can be included in the same model. Okay, what can we say if we go a little bit more in details in this type of tools? It looks great, but if you look at the formulation that is behind the graphical interface, fundamentally it's based on I would say, the engineering approach, the practical approach. So this means that you want to represent a motion. The first thing is you parameterize a motion, and then you can apply any discretization scheme you like, and you circumvent all the complexity of differential geometry. Okay, so the advantages of this approach, we see that it's a quite mature technique. We have nice tools. You can reuse standard discretization technique. But there are some disadvantages. And these are the following. So first, because we first parameterize and discretize, then we lose the link with the geometry. So it turns out that it's quite difficult to preserve some key properties of the solution. And one of them is objectivity or frame invariance. And so in this technique, you should be very careful if you want to implement this in the software in order to guarantee objectivity. This becomes very technical. And also what we have in this, nonlinear finite element method, we have a lot of locking problems. And these locking problems, actually, they are a consequence of, that's my interpretation at least, of this strategy that you first parameterize and then you discretize. And, but okay, my predecessors who developed the tool, they spent a lot of time, a lot of effort, and they could fix these problems, but they had to implement some numerical tricks. So it works when you want to deal with simulation, but if you want to touch a bit the software to make it do another job, like solving inverse problems, it's getting quite difficult. So the question now is, okay, we have a great tool which allows to do direct simulation, but is it really appropriate when we want to deal with inverse problems in robotics? Because in inverse problems, usually you're interested in more intrinsic properties of the solution. And we also know that inverse problems are more complex and more sensitive. So I tried this. That was my first trial when I was a PhD student, and actually it got very complicated. And so that was my motivation to look at alternative solution and go back to the theory. Okay, that's my personal experience with differential geometry. So I have an engineering background. So when I was a PhD student, I was really wondering whether this tool was for me because of my lack of background in mathematics. But I was attracted by the elegance of the approach. And so then after the PhD, I really started to study more on that. And I studied some references from different fields. And what was quite striking is that, all these people, actually they speak the same language in the end. And I thought that it was really worthwhile to invest on these techniques. And so in between, I did some contribution, and now the perception that I have from the engineer who have to, who get interested in this approach, is that, well, they're attracted, but still the abstraction level that is required to understand this method is rather high. So we have to do something. I think it's a collective effort that we have to do to reduce the abstraction wall, or maybe we have to build a staircase or something to help engineers. Okay, so the idea that I pursued then was to start from this finite element approach, because, well, I think it's a very powerful technique, this nonlinear FE approach, because it's really general. You can include many different types of bodies, rigid bodies, flexible bodies, joints. So it's great in principle, but I wanted to look at it with the differential geometry viewpoint. And the idea was to consider that the motion of the system is represented by frame transformation. Okay, so here you see all these structures are represented using, well, we have the inertial frame, of course, but we also have local frames. So in rigid body dynamics, so we can attach one local frame for each rigid body, and this allows us to follow the rotation and the position of the rigid body. If you have a flexible body, like a beam here, you can also define for every point of the center line, you can attach a local frame, and this will represent the position and orientation of the cross-section. This also works for shell. Then at every point of the mid-surface, you define a local frame, which will give you the information about the position and orientation of the normal director. Okay, so everything is in this frame transformation between the local frame and the inertial frame. And these frames, this frame transformation, we will consider them as elements of the group of rigid body motion, the special Euclidean group. Then in this Lie group formalism, you really have the choice to represent everything either in the inertial frame or in the local frame. And usually people in mechanics, they choose the inertial frame representation. Here, what we suggest is that the Lie group approach, or the differential geometry framework, it really simplifies the possibility to use the representation in the local frame. And so we decided to explore this approach, to represent all the dynamics in the local frame and not in the inertial frame. And I will try to show you that it gives quite interesting properties. And of course, then we exploit the discretization schemes on Lie groups and manifolds. Okay, I want to discuss a bit further this local frame modeling approach. And to begin smoothly, I propose to study the classical example in mechanics. This is the rotation of a top around a fixed point. Okay, so R is the rotation matrix. Omega is the angular velocity vector. We can put it on a skew symmetric matrix like this. And here you see we have the velocity relationship between the time derivative of the rotation matrix and the angular velocity. And here we have the Euler equation, which represents the dynamic equilibrium. But usually the Euler equation, people in mechanics, they choose to represent it in the local frame. Okay, so we do that also. So omega is the angular velocity in the local frame. J is the inertia tensor in the local frame. And on the right-hand side, we have the torque that results from the gravity force, also expressed in the local frame. So what we have here is actually a differential equation on a Lie group, because the rotation matrix evolves on the Lie group SO3, and the angular velocity matrix is an element of the Lie algebra. And so if we want to solve this equation numerically, well, we can use Lie group time integration scheme. And just to mention the simplest possibility, this would be the Lie group Euler explicit method. You see for the angular velocity, it's a simple Euler explicit scheme. And for the rotation, you need to use the exponential map because you want to guarantee that the result of this operation is a true rotation matrix. But the exponential map, we have an analytical form when we deal with the rotation group. So you can really implement that efficiently, and it works very well. And this can be extended to higher order time integration schemes. Okay, so that was for a system with only rotation. But we have rotation and translation, right? We have a frame. We need to represent frames. And so the way we represent frame transformation is using 4x4 transformation matrices like this one, which includes a rotation part and a translation part. And these matrices, well, we say that they evolve also on the Lie group, which is the Lie group SE3. And then we can also have the velocity representation as we had the angular velocity for the rigid body. Let's look what we get in this case. So we can have the same representation with this velocity matrix V tilde, which include actually a rotation part, which is as we had for the angular velocity here, and omega is also something in the local frame. But we have also a contribution for the translation part. And if you just manipulate simply the equation, it turns out that the velocity u is actually the velocity, the linear velocity, but represented in the local frame. So with this framework, it's very natural to represent velocities or derivatives in the local frame. Okay, we can also represent the dynamics of the system in the local frame. So these are the Newton-Euler equation of a rigid body. You have the translational equilibrium and the Euler equation that we saw earlier. And our approach relies on the representation of these equations in the local frame. Okay, so we do that for the rotation, but also for the translation. So everything here is represented in the local frame. So that was for the rigid body, but we are interested in flexible bodies. Okay, so I will introduce what we do to model flexible beams as an example. This is a very classical problem. I cite here the famous paper by Simo and Vukoc, which is really a highly cited paper. And the number of citations reflect, I would say, the attention of the community. And so a lot of people have worked on these nonlinear beams models. It's a very complicated formulation that you need to address the problem. And it's recognized in the community that the main point is to represent the strains. Because the strains are represented by nonlinear formula as soon as you have large rotation. So let's try to apply our formulation using these 4x4 transformation matrices, and let's try to evaluate the strains. So the first step to get the strain is to compute the gradient of this field of matrices, and we represent the gradient as we did for the velocities. And we have this gradient here. It's a matrix, a skew-symmetric, a matrix in the Lie algebra, F tilde. And then the question is, what is the relationship between this gradient and the strain? Well, it turns out that the relationship is as simple as this one. It's a purely linear relationship. So once you have the gradient computed using the Lie group machinery, you have almost a direct access to the strain, which is great. And so all the nonlinearity here is actually taken into account by the differential geometry operators. Then we need to define shape function for our beams. Okay, imagine that we have one node here and another one here, and we want to interpolate. Well, we apply the Lie group machinery. So first we compute a discrete gradient. It's like a finite difference, but we need the inverse of the exponential map, so the logarithm here. And we get our discrete gradient, and then we have this nice interpolation formula with the exponential map. Very simple. Then what we can do is a geometrical interpretation. It turns out that with this interpolation, we define shape function as an helicoidal interpolation of the motion, which is very appropriate for this type of problem. So these shape functions are actually geodesic curves, because we use the exponential map. And it's also by construction frame invariant. And it turns out that in the formula you see here, we only involve the relative motion between HB and HA. So the computation is completely insensitive to the global motion. It's only sensitive to the local displacement within the beam. And the same property will be inherited by all operators that are involved in the computation of elastic forces, because the strains only depend on the relative motion, the force, the elastic force only depends on this relative motion, the tangent stiffness, same property. And so everything is proportional to this relative motion in the beam. So this means that if you refine the mesh, typically you reduce the relative motion in each element of your mesh. So you reduce the nonlinearities by mesh refinement. Well, this is a nice property. So an example of a dynamic analysis. So this is a beam like an helicopter blade, if you want. So it rotates with several turns. And on top of that, there is a vertical motion. So we solve it in time using a Lie group time integration scheme. And if you think about it, we represent the motion in the local frame of the beam. But here, this beam has very small vibration and large overall motion. So for an observer that follows the motion and that is fixed to the beam, the problem is almost linear. And so that's the reason why we can compute the iteration matrix only in the first time step And then we keep it constant for the whole simulation. So you save a lot of computational cost, especially when you use implicit time integration. You can evaluate this matrix and factorize it only once and keep it for the whole simulation. And on top of that, we don't have any shear locking. So we did not have to use any trick. Naturally, the method is free from shear locking. Another example is the full roll-up of a beam. So this means we really make the full turn. And we use a coarse mesh, only 2 elements. So actually here it was not a beam element that was used, it was a shell, but well, it's roughly the same story. So this means that in each element you have half turn, right? And so we were able to solve this problem with this coarse mesh without any problem. And then we tried to skip the update of the tangent stiffness matrix. And in this case it doesn't work. You cannot apply the full load and get the answer. What we had to do was to divide the loading in 2 steps. So you first apply half of the loading and then the other half, and then you manage with this very coarse mesh to get the correct solution. And to see the mesh dependency, we tried the same problem with a slightly finer mesh. So we just have 4 elements. And again, we do not update the iteration matrix. And then we have better convergence, and we do not need to divide the loading into 2 steps. And again, there is no shear locking in this case. So this also works for shells. So here it's just to reproduce a standard test case for shells. And for shells have even more locking problems than beams. And again, with the formulation and the proper interpolation on the Lie group, we had no shear locking problems. Okay, so that was for the heart of the modeling approach. Everything is modeled and represented in the local frames, and then we have these nice properties. And then I will illustrate that we can solve also problems in robotics that would be very hard to solve using standard techniques. And I will address inverse dynamics problems and structural optimization very briefly, but just to show you what we can do. So here it's a problem where we want to control the motion of this end effector. So it's a robot which is fixed on the top. And so the end effector is here. And the motor are here. And in the model, we have to account for the vibration of the last 3 links. And so the question is, what are the torque that I need to produce a certain trajectory? So it's an inverse dynamic problem, but the problem is underactuated because you have the vibration modes of the machine between the input and the output. So the way we formulate the problem is as an optimization problem. So we have a cost function which represents the amplitude of the vibration over the trajectory. And this cost function should be minimized under the constraint that the equation of motion, well, I skip you the details, but these are the equation of motion in the Lie group. And they should be satisfied for all time. And in this equation, we also include the prescribed trajectories, the fact that we want the end effector to follow a certain trajectory. And we solve it using a direct transcription method, which is adapted to the Lie group framework. And it's fundamentally a gradient-based optimization approach. And these are some more details about the problems, but I can skip it. But what we obtain is, okay, we compute the inverse dynamics, either using a rigid model or using the flexible model. And you see that we do not get the same solution when we look at the joint motion. And when we look at the trajectory, so the reference is in black, you see that when we use the correct inverse dynamics, including the flexibility effect, we are able to track correctly the trajectory. When we do not account for flexibility, we are completely off the trajectory. And the convergence is done in a rather limited number of iterations. And we did also some experiments on a robot that we have in our lab, just to show you that the method also works in practice. So it's a cobot, so it's a collaborative robot. The movie. Sorry, the vibration was not physical, it's due to the movie. Let's try again. Yeah, it's better. So what you should see is at the end of the trajectory, you should see that if you use the solution from the rigid model, you have much more vibration at the end. If you, maybe I play it again. Okay, so this demonstrates that if you have a flexible model of your machine, you can really track a trajectory despite the vibration in the machine. Okay, if you are able to model vibration, you can also use these models for optimization, for structural optimization. So in this case, well, it's a bit academic example, but we have a two-link manipulator. And what we want to optimize are some parameters of the beams. We have 4 beams here, and we want to optimize the design of these, the section of these beams. Okay, so the problem is formulated as a weight minimization. So we want to minimize the weight of the machine, and we have a constraint on the trajectory error, on the stresses in the system at every time, and in a certain range of the variable. And again, using our approach, the differential geometric framework, we were able to solve the problem quite fast. And you can see the weight reduction that we can achieve with different versions of the optimization technique. But in the end, it works quite efficiently. So this brings me to the conclusion of the talk. So we have seen that flexibility should be considered in many applications in robotics. That there are some very powerful methods in multibody dynamics which are not appropriate once we talk about inverse problems in optimization and control. And so we have discussed this local frame formulation, which allow, actually the idea is that finally we simplify significantly the formulation and the algorithm with this approach compared to what is done with the parameterization-based technique. And yeah, there are some nice perspectives, of course, and this is the end of my talk. Thank you for your attention.
Okay, thank you very much. We have time for a few questions.
Very nice talk.
Thank
I
you.
just wonder, you are using legal structure that seems to be quite important in your approach. But you did not say anything about other geometric properties like preserving energy or simplicity and things like that. Is that something you have been looking at?
Yeah, it can be important in some cases, but I think that first you need the correct framework. So for me, the energy consideration is not the top priority, because anyway, in this practical application, we have physical anticipation that is present in the model, and so to have exact energy preservation is not a goal in itself. I think that the advantage of energy preserving scheme is about the stability, the numerical stability, that you can prove that you have a stability property regardless of the time step. I would say this would be the most important property that we would like to have here. But with the method that we use here, we can prove linear stability, which is already a good sign. But yeah, maybe as a perspective, it would be interesting to look at this method in order to have also these good stability properties.
I think we have time for one more quick question.
So in your robot example, you were tracking a reference solution.
Yes.
Right? This was not encoded in the objective function, but in the constraints.
There were two examples. Yeah, indeed. It's in the constraints. Yes.
Kind of DAE system?
Yes.
You also mentioned something with Lagrange multipliers?
Yes.
Yeah.
Yeah. That's a DAE. So we have a DAE on the Lie group.
And what is the index of that one?
In our case, it's 3.
Okay.
So the thing is, when you have this type of server constraints, you could have higher order, higher index DAEs. But here in the example, and the method that we have developed, it works well for index 3, and we did not test for higher order index. But we could have index 5 or 7. Yeah, this could be the case. But for that, we have no experience for the moment. Yeah.
All right, let's thank our speaker again.